Welcome to the New Quantum Era. I'm your host, Sebastian Hassinger, speaking to you from Paris this time, where I've been attending the Q2B conference. All the Q2B conferences are great, and I really appreciate the effort that QCware has put into them all these years, but I really enjoy the Q2B Paris edition, and not just because of the appeal of the city itself. It's great to spend time in the quantum community here in Europe, and especially the vibrant community here in France. The public sector efforts in France have been really impressive, with great coordination across strong university research labs, the public sector labs, the federal government, and the private sector as well. There's a lot of really great work going on, in particular in hardware, and today we're going to be talking with the co-founder of one of those hardware companies. Pierre Desjardins is the co-founder and CEO of C12, a company that's working on a unique variety of silicon spin qubits. We previously learned about spin qubits when we talked to Andrew Dirac, the CEO of Dirac, but the ones that C12 are working on are quite unique in a way that is foreshadowed by the name itself. So while I was here for the conference, I took the opportunity, with the help of Lydia Baril from C12, to go to their beautiful new offices right by the Pantheon and record an interview. Pierre's story is quite unique. He's one of the few quantum hardware startup founders that doesn't have a PhD, an attribute I share with him, though he did get a master's in physics from Columbia, so he's more of a scientist than I. He founded the company with his twin brother, Mathieu, and he's building the hardware based on nanotubes made of carbon-12 atoms. We'll dive into how C12 is creating ultra-pure, highly coherent qubits using these suspended carbon nanotubes, and talk about how they're developing laboratory experiments into real-world devices. Pierre shared with me the company's focus on material science, the unique combination of microwave controls with electron spin qubits, and how their quantum bus may be the key to their scalable, error-corrected quantum computing. I learned a lot from our conversation, and I hope you will too. So let's jump right into my conversation with Pierre Desjardins. I would love to start by hearing a little bit about how you got started, how you got to where you are as a founder of a quantum computing company now.
So a rare co-founder of a quantum startup company without a PhD.
Yes, that's notable.
And another rare thing is that I co-founded C12 with my twin brothers.
Right.
So it's good, actually, to have like two twins at the head of a quantum startups, I think. All these
I'm sure
mysterious
the jokes have been very predictable, I'm sure.
So we graduated from the same engineering schools, and then Mathieu, so Desjardins, my twin brother, was a PhD student in the laboratory of physics at the École Normale Supérieure. And this is where they made all this incredible scientific experiment and discoveries about carbon nanotubes, quantum electronics.
Right.
I think we will cover this, later. And then when he was a postdoc in Takis Konto's lab, this is when he had we could say the vision and the ambition to convert all this scientific discovery into one super cool application, which is building a quantum computer.
Right.
And then it was in 2020 that we decided to incorporate the company and really to supercharge what was developed in the lab the years before. So we just celebrate the 5 years of C12.
Congratulations.
And, when you are in a deep tech and even quantum tech with such ambitious goals, and when also all the developments take a very long time, because we know building a quantum computer is super hard.
Yes.
So being here 5 years later with such a great company, the team is just so I love working with them. It's great. So it was a very good time to enjoy.
So was it hard for him to convince you that this was a good idea to go try to build this company?
The good thing is that we were during COVID. So I stopped working.
Nothing better to do.
Exactly. I stopped working on my previous job, which was like consulting, and I had like a day long of like just reading quantum computing, and so I did my kind of due diligence on like carbon nanotube qubits, and it's quite fascinating. The more you dig into this technology, the more you understand why this is just the way to build a quantum computer. So then I was like very strongly convinced.
You were a convert. Yeah. I think that is definitely critical to any founder of a quantum hardware company to be convinced that they have the way. Everybody needs to have that.
I mean, you're going to dedicate your life to building this, so it better be.
Yeah, and there's so many challenges and so many unknowns. You really have to have that conviction that you're on the right path. So you already mentioned carbon nanotubes, but what you're building is a variation on spin qubits. So there's a number of companies and a lot of research in silicon spin qubits, which are using the spin of electrons, individual or very small groups of electrons, depending to capture that two-level system for the qubit. But you're doing it in a different way that's quite unique. So tell me about that.
We are in this, indeed, a big family of spin qubits where we manipulate, as you mentioned, the spin of a single electron. And I mean, first you have like different qubit modalities, but even within the spin, it's a whole different kind of zoology. So you used to have like 3-5 material like gallium arsenide, but then people understood that it was like way too noisy, and so now you have like people building spin qubits very close to the CMOS, so silicon spin qubits. You have germanium now, so but then in the heterostructure, so some people are doing like germanium, silicon germanium, and others are doing silicon germanium.
Right.
You have FDSOI, and then you have also like carbon nanotube. So carbon nanotube might looks like wow, super strange. It is, of course, but it's just interesting to understand also like. For the moment, like there is like many flavors of spin qubits.
But I guess what's interesting to me is you're fabricating these carbon nanotubes separately and then affixing them to the chip surface, right? I mean, you're testing them for impurities and making sure they're perfectly formed, and then attaching them to a chip surface. So that seems like a really unique challenge.
So the goal and the vision about using carbon nanotubes is to have the system have the purest material to trap the electron, and something with the lowest disorder material. So that's why we are using a material that is really like what we call we call them single wall carbon nanotube. So it's just like one carbon nanotube, and the wall of this nanotube is just one layer of carbon atom. So
incredible.
In terms of like what you can, it's much. It looks like at the end we trap the electron into like a macro molecule. So it's extremely low density of material, and we do that exactly the way you are describing it. So we fabricate the carbon nanotube on one side, we fabricate the silicon chip on the other side, and at the end of the process we integrate the carbon nanotube on the silicon chip. And because we are able to doing the assembly as a last step, indeed at the end the carbon nanotube is suspended over the gate electrode. So as Mathieu described it, it's like the closest realization of a spin qubit in vacuum.
Interesting.
So this is really how we want to build like super high quality qubits.
And so how many carbon atoms make up each ring of the tube?
So then below the carbon nanotube, you have electrode, and like other spin qubit technologies, so we trap the electron into like double quantum dots or quantum dots.
Right.
So then at the end, the like really active part, or the part that of the carbon nanotube that is used is only like a few micron.
And do you? I mean, is there a specific number of carbon atoms that make up the circumference of the tube?
I know where you are coming. Like why 12? Why C12?
Yeah. That's what I was guessing.
It doesn't come from the number of atoms that are forming the circumference of this tube. And here it's very interesting also because what you mentioned here is like carbon nanotubes. They have like each of them. They have a unique number characterizing them as chirality, and we are actually selecting the right carbon nanotube to make the best qubit. But on this side, fortunately, we can have like a wide range of chiralities that work. The way does the 12 from C12 coming from is that we are using isotopically purified form of carbon.
Okay.
So we only are using carbon 12.
Okay.
Like silicon is only using, for example, silicon 28. So it's even number.
Yeah.
And so there is no magnetic spin, no nuclear magnetic spin.
Right.
So it's contribute to make the material really perfect.
And that makes intuitive sense that would make for a very noise-free kind of environment for that single electron. And that, it makes a lot of sense that, as you were saying, that all of those explorations of different materials and spin qubits, the central challenge is getting an environment for that single electron or small group of electrons that is that's as quiet as possible. Basically, it's isolated but controllable. So is that nanotube is providing that isolation, but it's also allowing the control of the electron within the nanotube?
Yes.
Yeah.
So one, for example, like a number to share about the carbon nanotube is for any kind of spin qubit, the worst, let's say, noise, the thing that will create the most perturbation, is noise coming from charge. Charge that can be like a fluctuator, and charge that can be trapped close to the qubit, so it's encapsulated in this like charge noise.
Yeah.
And so on our device, we are able to measure the level of charge noise that is seen by the qubit. And here we have the lowest charge noise if we compare to any kind of spin qubit.
Right.
And this is really because with this like suspended architecture, we screen any kind of charge that we can have. And this is why we have this profound conviction that the winning criteria to build large-scale quantum computer is very fundamental and very at the heart of the design choice that you made at the beginning. For example, in the material that you choose for encoding your qubit. And now you mentioned that then indeed how we solve this like quantum paradox, because when you have a super isolated qubit, if you, as you mentioned, cannot address it.
This is the problem with the photonics, right? They love to say that they don't decohere, but it's because they don't react with anything. So, yeah.
So this how we actually address our qubit. And here we also are using a very unique approach, at least compared to other spin qubits, because in a way we drive our qubit the same way superconducting qubits are driven.
So microwave pulses.
So we use microwave pulse.
Interesting.
And so what we introduced, and it was one of the core discovery of the Laboratory of Physics at the École Normale Supérieure is that you can use this like physics principle of spin-photon coupling to drive spin through a microwave photon.
Okay.
So this
so you are using photons.
Microwave.
Yeah.
they don't suffer the same loss.
Right.
Hopefully.
Yes.
Fortunately.
Yeah.
And no. And the first experimental proof of spin photon coupling was done in the physics lab at École Normale Supérieure, and we really are using this principle to build our quantum computer. So what we introduce and is the concept of a quantum bus. The idea of a quantum bus is to use a superconducting element to make the interconnects between the different spin qubits. And this is where it's fundamentally different from other architecture. Is for other architecture, you connect the spin between each other because they are close to each other and like part of their wave function overlap.
Yeah.
And so you are constrained with nearest neighbor.
Right. Or you have to do shuttling, which then brings in all of the
challenges.
Yes. Yeah.
And the idea with the quantum bus is really to be able to do any kind of interconnects between qubits.
Right.
Even like if your qubits are not nearest neighbors. So it has like incredible benefits. The first one is that for in what we think is that it's really the only way to scale spin qubit, because if you are stuck with the nearest neighbor architecture, you cannot actually wire all your qubits.
Right.
So it's what we call the fan-out problem.
Yeah.
And
I mean, especially when you start looking at error correction, the topology needs to match the code that you're going to use, surface code or Floquet or whatever. And if you're stuck with just a very small number of nearest neighbor kind of connections, it's really, really challenging.
Yeah, you made a very, very extremely relevant point. It's why we think that all of this is important, like having high quality qubits, having like high connectivity between the qubits is at the end, because then it's a platform that will be able to support much more sophisticated quantum error correction code. And when we say sophisticated, it's like with a much lower overhead. And on this we have like it's interesting. We started the company with this very materials oriented background, so we are all focused on, and we are still about delivering the best kind of qubits, like mastering manufacturing and production processes. And we decided to launch some works about quantum error correction like quite late. Only started to work on this topic last year. But it's also good because like the field of quantum error correction is so progressing so fast,
very fast, that
probably like the code that we are currently working on for our architecture did not exist.
Right.
2 years ago.
But before we move on to the error correction, I'm still curious about so how do you address the individual qubits on that bus? What's the addressability? Is it different frequency resonances, or like how does that work?
So we have one line that directly connects to the qubit, and then can actually then drive the qubit. And then it's also why with like our technology it works to have a quantum bus, because the concept of quantum bus was also tried for also superconducting qubit, because it solves a lot of problems. You have like a high connectivity.
Right. This is what I'm wondering, because they've looked at either tunable connectors or having the being able to turn on and off the superconductivity, so you can essentially isolate the qubits from one another when you don't want them to interfere with one.
And this is why it works in our case, is that we have a very good tunability and we can really tune the coupling between the quantum bus and the spin qubit. So it's actually very easy to understand how it works. So when the qubit is, we can say on, so connected to the quantum bus, the qubit is really hopping between the two sides of the double quantum dots, and then it acts like a very small antenna and connecting to the bus. But when you don't want to have this coupling, you localize the electron into one side of the double quantum dot.
Okay.
And so then you have a off mode, memory mode, where you can also increase a lot the coherence time because the electron is much more isolated.
Right.
So this is how this concept of quantum bus is
interesting.
Is working.
And are the two dots in the double dot system, are they on the either end of the nanotube? Is it sort of physically separated, or is it a different sort of design?
It's so you have below the carbon nanotube, you have a set of electrodes, and this is how they design, how we design the double quantum dot. So
and quantum dots themselves, there's some challenges around other ways of achieving spin qubits around the lifetime of dots, right? There's sort of durability issues with some of the ways that you can fabricate dots don't have a tremendously long lifespan, essentially, as a material. Is that something that
No, we don't suffer from this. Yeah.
I was assuming because of the purity of the carbon, that probably...
and our chips travel, and we send some of our chips to collaborators. They measure them for years, and
that's great.
It's actually something where we make a real difference, is that it's the stability of the qubit over time. So when we have calibrate our qubits, then the drift is very very small.
Wow!
So it's not like with superconducting qubits that
right.
Each day you have to also recalibrate.
It sounds like you've sort of got the best of both worlds with the flexibility of the connectivity of superconducting qubits, but then it's less of an analog system than a superconducting qubit is, where there's constantly calibration and drift and all sorts of
that's I think that we have really the speed of in terms of gate duration,
right?
That is very similar to what you have in a superconducting qubit, but we really leverage the intrinsically stable spin quantity, and also of course the addition of this very pure material to have a very long coherence time.
That's fantastic. So that's amazing. It's great you got to 5 years. As a last question, what do you see as the biggest challenges for the year ahead? Let's just look 1 year at a time.
So 2 years ago, last year, sorry. Okay. Last year, we realized the first qubit operation on our qubits. In a way, we started with really reimagine how quantum computers are built, and we really started from to first build the fundamental bricks of our technology. So we presented our results in Nature. So we really have ultra long coherence time of a spin qubit connected to the quantum bus on one qubit, And what we are currently focusing is to realize quantum gates between two qubits.
Right.
Two then distance qubits.
Right.
So it's a very different kind of gate than for other spin qubit, because in this case you really have like a spin-spin interaction mediated by a microwave photon.
Yeah.
And this is, I think, a very important milestone for C12, but I think also for industry, because it really like opens the doors for like scaling this kind of technology.
Right.
And we know that also like IBM is working on this long distance qubit quantum gate.
Yeah.
So what I wish is that we can announce it just before IBM.
Very good. That's great. Well, thank you so much for your time today, Pierre. This has been really interesting. I really enjoyed it.
Thank you, Sebastian. It was a pleasure also.
Great.
Thank you.
Thank you for listening to another episode of the podcast, a production of the New Quantum Era, hosted by me, Sebastian Hassinger, with theme music by OCH. You can find past episodes on www.newquantumera.com or on Blue Sky at newquantumera.com. If you enjoy the podcast, please subscribe and tell your quantum curious friends to give it a listen.